Okay, good morning. Today we'll see remaining part of the temperature measurement. In that, first of all, we'll see constant volume thermometer. The constant volume thermometer uses an inert gas in place of mercury, and the principle of its working is the increase in pressure of the gas with increase in temperature at constant volume. However, the volume of the system, that is that of bulb, capillary, and the Bourdon tube, does not remain constant and increases slightly due to the increase in pressure, and in addition the volume of the bulb also increases due to increase in temperature. Gas filled systems operate over a range of -130 to 540 degrees Celsius with linear ranges as large as 500 degrees Celsius. However, its disadvantage over the liquid filled system is that the pressure developed for a given temperature change is smaller, and further ambient temperature compensation is more difficult. The accuracy of these instruments is of the order of ±1% at lower ranges, that is up to 300 degrees Celsius, and ±2% above this range.
हॅलो सर ते गणेशचं माईक म्यूट करा ना सर.
Next is vapor pressure thermometer. The system in the vapor pressure thermometer is filled partly with liquid and partly with vapor of the same liquid, so that there is a liquid vapor interface in the bulb. The liquid vapor system does not have any error as long as free liquid surface exists in the sensing bulb. This is because such a system follows one of the Dalton's law of partial pressure, which states that if both liquid and vapor are present, there is only one saturation pressure corresponding to a given temperature. The general usefulness of the vapor pressure thermometers is restricted due to the limited number of liquids providing suitable saturation vapor pressure ranges. These include mostly hydrocarbon type of fluids like ethane, ethyl alcohol, ethyl chloride, methyl chloride, chlorobenzene, toluenes, pentane, ether, acetone, etc. The scale range is usually of the order of 100 degrees Celsius, and accuracy is up to ±1% of the differential range. Further, the temperature is roughly a logarithmic function of the temperature, that is log of P is equal to A minus B divided by T, and therefore the scale of the vapor pressure thermometers is noticeably non-linear. Now next is electrical methods. Electrical methods are in general preferred for measurement of temperature as they furnish a signal which can be easily detected, amplified, or used for control purposes. There are two main electrical methods used for measuring temperature. They are first thermoresistive type, that is variable resistance transducers, and second thermoelectric type, that is EMF generating transducers. Next is now we will see electrical resistance thermometers. In resistance thermometers, the change in resistance of various materials, which varies in a reproducible manner with temperature, forms the basis of this important sensing technique. The materials in actual use fall in two classes, namely conductors, that is metals, and semiconductors. In general, the resistance of the highly conducting materials increases with increase in temperature, and the coils of such materials are called metallic resistance thermometers. Whereas the resistance of semiconductor materials generally not always decreases with increase in temperature. Thermosensitive resistors having such negative temperature characteristics are commonly known as NTC transistors, or sorry, NTC thermistors. Now this is the temperature versus specific resistance graph for the thermistor and platinum. If you will see, as the temperature increases, specific resistance of thermistor decreases while specific resistance of platinum increases. Now next is metallic resistance thermometers or resistance temperature detectors, RTDs. Metals such as platinum, copper, tungsten and nickel exhibit small increase in resistance as the temperature rises because they have a positive temperature coefficient of resistance. Platinum is a very widely used sensor and its operating range is from 4K to 1064 degrees Celsius. Because it provides extremely reproducible output, it is used in establishing international practical temperature scale from 13.81 Kelvin to 961.93 degrees Celsius. However, for the measurement of low temperatures up to 600 degrees Celsius, RTD sensor is made of nickel. Further, for ranges of temperature below 300 degrees Celsius, the sensing element is fabricated using pure copper wire. Metallic resistance thermometers are very suitable for both laboratory and industrial applications because of their high degree of accuracy as well as long-term stability. In addition, they have a wide operating range and have linear characteristics throughout the operating range. However, the limitations of the RTDs are low sensitivity, relatively higher cost as compared to other temperature sensors, and their proneness to errors caused due to contact resistance, shock, and accelerations. Metallic resistance thermometers are constructed in many forms, but the temperature sensitive element is usually in the form of a coil of fine wire supported in a stress-free manner. A typical construction is shown in figure where the wire of metal is wound on the grooved hollow insulating ceramic former and covered with protective cement. The ends of the coils were welded to stiff copper leads that are taken out to be connected in one of the arms of the Wheatstone bridge circuit. In some cases, this arrangement can be used directly in the medium whose temperature is being measured, thus giving a fast speed of response. However, in most applications, a protective metal sheath is used to provide rigidity and mechanical strength. Alternatively, RTD sensors may be fabricated by depositing the thin films of platinum, nickel, or copper on a ceramic substrate. These thin film sensors have the advantage of extremely low mass and consequently more rapid thermal response. Therefore, this is the figure of resistance temperature detector. See that this is the rod, it is having groove so that the coil is wound on the groove. Now next is semiconductor resistance sensors, thermistors. Thermistor, shortened form of the words thermal resistor, is a thermally sensitive variable resistor made of ceramic-like semiconducting material. They are available in a greater variety of shapes and sizes, having cold resistance ranging from a few ohms to mega ohms. The size can range from extremely small bead, thin disc, thin chip, or vapor to a large sized rod as illustrated in figure 6.6. Therefore, these are the various configurations of the thermistor. Unlike metals, thermistors respond negatively to temperature and their coefficient of resistance is of the order of 10 times higher than that of platinum or copper. Thermistors are fabricated from the semiconducting materials, which include the oxides of copper, manganese, nickel, cobalt, lithium, and titanium. These oxides are blended in a suitable proportion and compressed into desired shapes from powders and heat treated to recrystallize them, resulting in a dense ceramic body with the required resistance temperature characteristics. Thermistors have the following advantages for temperature measurement. First, a large temperature coefficient which makes the thermistor an extremely sensitive device, thus enabling accuracy of measurement up to plus minus 0.01 degree Celsius with proper calibration. Second, ability to withstand electrical and mechanical stresses. Third, fairly good operating range which lies between minus 100 and 300 degrees Celsius. Fourth, fairly low cost and easy adaptability to the available resistance bridge circuits. And fifth, the high sensitivity and the availability in extreme small sizes of the size of a pinhead enable a fast speed of thermal response. Thus, these devices are extremely useful for dynamic temperature measurements. However, the disadvantages are a highly nonlinear resistance temperature characteristics and problems of self-heating effects, which necessitate the use of much lower current levels than those with metallic sensors. Therefore, these are the different shapes of the thermistors: bead shape, disc shape, rod shape, IC type of shape. Now next is the thermocouple materials. The choice of materials for thermocouples is governed by the following factors. First, ability to withstand the temperature at which they are used. Second, immunity from contamination slash or oxidation, etc., which ensures maintenance of the precise thermoelectric properties with continuous use. And third, linearity characteristics. It may be noted that the relationship between thermoelectric EMF and the difference between hot and cold junction temperatures is approximately of the parabolic form. E is equal to AT plus BT square. Thermocouple can be broadly classified in two categories. First, base metal thermocouples, and second, rare metal thermocouples. Base metal thermocouples use the combination of pure metals and alloys of iron, copper, and nickel and are used for temperature up to 1450 Kelvin. These are most commonly used in practice as they are more sensitive, cheaper, and have nearly linear characteristics. Their chief limitation is the lower operating range because of their low melting point and vulnerability to oxidation. On the other hand, rare metal thermocouples use a combination of pure metals and alloys of platinum for temperatures up to 1600 degrees Celsius and tungsten, rhodium, and molybdenum for temperatures up to 3000 degrees Celsius. Typical thermocouples with their temperature ranges and other salient operating characteristics are given in table. Table characteristics of some thermocouples. Constantan is equal to copper or nickel. Chromel means nickel, chromium. Alumel means nickel plus aluminum. For special purposes where high sensitivity is needed, thermocouples may be attached in series. The output is then the numerical of the voltages expected from each of the single couples. This is commonly known as thermopile. When connected in parallel, a pump of the thermocouples will be a real, that is a numerical average of the individual ones, provided the resistance of each individual thermocouple being the same. The following are the advantages of thermocouple sensors. First, thermocouple bead can be made of small size and consequently with low thermal capacity. In other words, dynamic response of sensor is fairly good. Second, they cost considerably less as compared to other thermal sensors, and further, they require no maintenance. Third, they are quite rugged type, that is, they can withstand rough handling. Fourth, they cover wide range of temperature, that is from -200 to 3000 degrees Celsius. Fifth, output signal is electrical and they can be used for indicating recording or microprocessor based control systems. Sixth, output signal, that is EMF, is independent of length or diameter of the wire. Seventh, they have good accuracy of the order of plus minus 0.2 to plus minus 0.75% of FSD. Eighth, they have excellent stability for a long period of time. Ninth, they can be conveniently mounted in a variety of temperature measurement situations. The thermocouple sensors, however, have the following limitations. First, inhomogeneity of composition of the thermocouple material and cold working of wires affect the sensitivity of the thermocouple. The required insulation covering while using them in conducting fluid, they require insulation covering. The output signal, that is EMF, requires amplification in most applications. Now next is radiation methods, that is pyrometry. All the temperature measuring devices discussed so far, that is pressure thermometer, thermistor or thermocouple etc, require the thermometer to be brought into physical contact with the body whose temperature is to be measured. This means that the thermometer must be capable of withstanding this temperature. In the case of very hot bodies, the thermometer may melt at the high temperature. Secondly, for bodies that are moving, a non-contacting device for measuring the temperature is most convenient. Thirdly, if the distribution of temperature over the surface of an object is required, a non-contacting device can readily scan the surface. For temperatures above 650 degrees Celsius, the heat radiations emitted from the body are of sufficient intensity to be used for measuring the temperature. Instruments that employ radiation principles fall into three general classes. First, total radiation parameter. Then next is selective radiation parameters. And third is the infrared parameter. The first is sensitive to all the radiation that enters the instrument, and the second only to radiation of a particular wavelength. Further, the infrared parameters employ the infrared portion of the spectrum by using a thermal detector to measure the temperature on the surface of the body. Now, first of all, we will see total radiation parameter. The total radiation parameter receives a controlled sample of the total radiation of a hot body and focuses it onto a temperature sensitive transducer. The term total radiation includes both visible, that is light, and invisible, that is infrared radiations. It may be noted that the wavelength of light in the visible range is from 0.7 to 0.72, sorry, 0.3 to 0.72 micrometer, whereas the infrared radiations are associated with relatively large wavelengths of 0.72 to 1000 micrometer. They require special optical materials for focusing. Ordinary glass is unsatisfactory as it absorbs infrared radiations. In fact, the practical radiation parameters are sensitive to a limited wavelength band of radiant energy, although theory indicates that they should be sensitive to the entire spectrum of energy radiated by the object. Figure shows a schematic diagram of the Fairy's total radiation parameter. It consists of blackened tube T open at one end to receive the radiations from the object whose temperature is to be measured. The other end of the tube has a sighting aperture in which an adjustable eyepiece is usually fitted. The thermal radiations impinge on the concave mirror, whose position can be adjusted suitably by a rack and pinion arrangement so as to get proper focusing of the thermal radiations on the detector disc S. The detector disc is usually blackened platinum sheet or foil and is connected to a thermocouple or thermopile junctions or to a resistance thermometer bridge circuit. Leads from the detector are laid out of the casing to a meter for measuring the thermoelectric EMF or the variation, the electric resistance of the platinum foil. The theory underlying the operation of total radiation parameters is that the rate of radiation from a body A, the source, to a body B, that is parameter, that is E and B, is given by the Stephens-Boltzmann law as follows, that is EAB, that is energy received by the parameter in watt per meter square, is equal to C into epsilon into sigma into TA raised to 4 minus TB raised to 4. C is a geometrical factor to adjust the relative shapes of the two bodies. E is the emissivity of the detector disc, which varies from 0.05 to 1.0 for the theoretical black body. J is the Stephen-Boltzmann constant and its value is 56.7 into 10 raised to minus 12 kilowatt per meter square into Kelvin raised to 4. TA and TB are the steady state absolute temperature of the source and parameter detector disc. Such parameters are usually calibrated against known temperatures in the range of 700 to 2000 degrees Celsius, where thermocouples and resistance thermometers cannot be employed. However, the errors arise from two sources in actual use. Any filtering material such as smoke, dust, gases, windows, etc., which were not present in the calibration, will reduce the energy received, hence cause an unknown error. Secondly, an error may be caused due to a surface having emissivity other than used in the calibration. Since the surface emissivities are not known very accurately and a change occurs with time due to oxidation, therefore the error due to unknown emissivity is usually not known. To reduce such uncertainties, parameters calibrated from time to time in actual use. In view of the troubles due to filtering and emissivity, the total radiation parameter is not a very accurate temperature indicator. However, it can be used to good advantage in fixed locations where the emissivity and optical paths are well known and constant. A typical use is a large furnace in metal industries. The signal is electrical and therefore can be used for control applications. Therefore, this is total radiation parameter. Now, selective radiation parameter. See that when equal brightness is there, you will not see the filament. The principle of this instrument is based on Planck's law, which states that the energy level in the radiations from a hot body are distributed in the different wavelengths. As the temperature increases, the emissive power shifts to shorter wavelengths. The Planck's distribution equation is where C1 is equal to 3.740 into 10 raised to minus 12 watt centimeter square. C2 is equal to 1.4385 centimeter degree Celsius. A is equal to wavelength centimeter. T is equal to absolute temperature in Kelvin. W is equal to energy level associated with wavelength at temperature T, watt per centimeter cube. The classical form of this optical parameter is the disappearing filament optical parameter or the monochromatic brightness radiation parameter. It is most accurate of all radiation parameters. However, its use is limited to temperatures greater than about 700 degrees Celsius since it requires usual brightness matched by a human operator. This instrument is used to realize the international practical temperature scale above 1064 degrees Celsius. It is obvious from Planck's distribution equation that for a given wavelength, the radiant intensity varies with the temperature. In the disappearing filament instrument shown in figure, an image of the target is superimposed on the heated filament. The tungsten lamp, which is very stable, is previously calibrated so that when the current through the filament is known, the brightness temperature of the filament is also known. A red filter that passes only a narrow band of wavelengths around 0.65 micrometer is placed between the observer eye and the tungsten lamp and the target image. The observer can see the lamp until the filament disappears in the perimeter target image. Lamp filament is there. The temperature calibration is made in terms of lamp heating current because of the mutual null balancing principle. The optical parameter is not useful. It is not usable for continuous recording or automatic control applications. However, it is more accurate and less subject to large errors than the total radiation parameter. The accuracy of such parameters is usually plus minus 5 degrees Celsius in the range of 850 to 1200 degrees Celsius. Further, when used in the extended range of 1100 to 1950 degrees Celsius, its accuracy is better than plus minus 10 degrees Celsius. Therefore, this is selective radiation parameter. When the filament is too dark, you will see the image like this. When the filament is too bright, and when the wavelength will match, you will see the equal brightness. Therefore, this is the end of this temperature measurement chapter.